Next bounding function notation is big omega notation, aka the lower bound. The big omega notation is used to describe the lower bound or the minimum possible running time of the algorithm. Definition: big omega of g of n is a set of functions f of n such that there exists positive constants c and n sub 0 such that 0 is less than or equal to c times g of n, which is less than or equal to f of n for all n greater than or equal to n sub 0. As you can see, this one is the opposite of big O. This time, c times g of n is always below or less than or equal to f of n, as you can see here. Let's say that this again is the graph running times of our algorithm. We just have to find a constant c times g of n, which is always less than or equal to f of n at some point n sub 0 to positive infinity. Again, c times g of n is always less than f of n starting at this point onwards. Therefore, we have a guarantee that it won't run slower than g of n. Again, we'd want to have a c times g of n that is tight to f of n. This one has a large gap, so we'd want a tighter bound. In this example, we have the same expression, n squared minus 3n, but this time, cn squared should always be less than or equal to it. So we simply have to find an n sub 0 and a c that makes this inequality true. For example, let's choose n is equal to 4, the same n as earlier. And maybe a really small c, like 0.00001. Again, it still should be positive. This would make the inequality true. Therefore, n squared minus 3n is indeed under big omega of n squared. Take note that, intuitively, this should be true for all n that we choose, that is greater than n sub 0. So if you find a larger n that makes this inequality false, then either that n is invalid or the inequality is really false.